right there is higher than the surface charge density here. Only if it is a sphere, of course, for spherical symmetry reasons, will the charge be uniformly distributed. If the electric field becomes too high, we get what we call electric breakdown. We get a discharge into the air, and the reason for that is actually quite simple. If I have an electron here, and this is an electric field, the electron will start to accelerate in this direction. The electron will collide with nitrogen and oxygen molecules in the air, and if the electron has enough kinetic energy to ionize that molecule, then one electron will become two electrons, the original electron plus the electron from the ion. And if these now start to accelerate in this electric field, and if they collide with the molecules, and if they make an ion, then each one will become two electrons, and so you get an avalanche. And this avalanche is an electric breakdown, and you get a spark. When the ions that are formed become neutral again, they produce light. And that's what you see. That's the light that you see in the spark. And so sparks will occur typically at sharp points, at areas where the curvature is strong, whereby the radius is very small. That's why the electric fields are the highest. How strong should the electric field be? Well, we can make a back-on-the-envelope calculation. If you take air of 1 atmosphere, dry air, at room temperature, then the electron, on average, will have to travel about 1 micron, which is 10 to the minus 6 meters, between the collisions with the molecules. It's just a given. On average, sometimes a little more, sometimes a little less. It's a random process, of course. To ionize nitrogen, to ionize oxygen, takes energy. To ionize an oxygen molecule takes 12.5 electron volts, and to ionize nitrogen takes about 15 electron volts. What is an electron volt? Well, an electron volt is a teeny-weeny little amount of energy. It's 1.6 times 10 to the minus 19 joules. Electron volt is actually a very nice unit of energy. Because once you have an electron, and it moves over a potential difference of 1 volt, it gains in kinetic energy. That's the definition of an electron volt. It gains 1 electron volt. It's the charge of the electron, which is 1.6 times 10 to the minus 19 coulomb, multiplied by 1 volt. And that gives you then the energy, 1 electron volt. And so, what it means then, let's assume that this number is 10 electron volts. So we only want a back-on-the-envelope calculation. So we want the electron to move over a potential difference delta V, which is roughly 10 volts, and we want it to do that over a distance delta x, which is 10 to the minus 6 meters. That's your 1 micron. And if that happens, you'll get this enough kinetic energy in the electron to cause an ion. So what electric field is required for that? That is delta V, the potential difference, divided by the delta x. So that is 10 divided by 10 to the minus 6. So that's about 10 to the 7 volts per meter. That's a very strong electric field. In reality, when we measure the electric fields near breakdown, it is more like 3 million volts per meter. But it's still very close. This was only a back-on-the-envelope calculation. So very roughly at 1 atmosphere air, room temperature, when the air is dry, we get electric breakdown at about 3 million volts per meter. When the ions neutralize, you see light. That's why sparks can be seen. They heat the air. They produce a little pressure wave, so you can also hear noise. If you had 2 parallel plates, and you would bring those plates closely together, and suppose they had a potential difference of 300 volts, then you would reach an electric field of 3 million volts per meter when the distance d is about 1/10 of a millimeter. So that's when you expect spontaneous discharge between these two plates. In practice, however, it probably will happen when the plates are further apart than 1/10 of a millimeter. And the reason for that is that there is no such thing as perfect plates. The plates have imperfections. That means there are always areas on the plate which are not flat, but are a little bit like what you see there. Small radius. And that's, of course, where the electric field then will be larger, and that's where the discharge will occur first. However, if you touch the door knob and you get a spark, you feel a spark, and you look at the spark and you see that when you're 3 millimeters away from the doorknob that the spark develops, you can pretty sure that the potential difference between you and the door was of the order of 10,000 volts, several thousand volts at least, because over 3 millimeters it requires 10,000 volts to get to 3 million volts per meter. When you comb your hair, or when you take your shirt off, you get little sparks, you can hear them, and if it's dark you can see them, and you can be sure that at the sharp ends of this hair, of the fabric, that you have developed electric fields of the order of 3 million volts per meter, and then you get the automatic breakdown. Now, of course, high voltage alone doesn't necessarily kill you. What matters is not so much the voltage to get killed, but it's the current that goes through you. And current is charge per unit time. And so in SI units, it would be coulombs per second, for which we write a capital A, which stands for ampere. The man who did a tremendous amount of research in this area, Frenchman. And so if you touch the doorknob, the instantaneous current may actually be quite high, maybe an ampere even, but it may only last for 1 millisecond. And so that's not going to kill you. We all know that when you comb your hair, that you don't die. And we also know that when you take your shirt off, even though you may hear the sparks, that's not lethal. So maybe in a future lecture we can discuss in some more details what it does take to actually execute someone electrically, which is very unpleasant, but nevertheless, we would have to evaluate how long the current should last, how strong the current should be, and then also during which parts of the body the current would cause lethal reactions. So I want to be a little bit more quantitative now and deepen our knowledge of the Van de Graaff. Slowly we're going to understand how the Van de Graaff works, and today I want to calculate with you how much charge we can put on the Van de Graaff and what the maximum potential is at the surface. If we charge up the Van de Graaff with charge Q, then the potential of the surface is an equipotential is Q divided by 4 pi epsilon 0 r. And the electric